You're probably all familiar with telescopes, and many of you maybe have even used one before. If we stare at the sky with just our bare eyes, aside from large objects like the moon, we can really only make out tiny pinpricks of light. Don't get me wrong, stars are gorgeous like this. I could stare at the night sky forever. But we also love looking at celestial objects up close when we can make out tiny details and learn more about them. You know that a telescope magnifies images of the sky, but have you ever thought about exactly how this process works to form these pristine images of objects so far away? Well, let's break down a few basic principles of optics and find out. As a quick side note, I'm really only going to be talking about refracting telescopes here. Reflectors, those are telescopes that use mirrors instead of lenses, are actually used substantially more today, and there's a couple reasons for that. Mirrors can be supported on the back, and whereas lenses, you have to be able to see all the way through them, so we can't do that, which makes them much easier to construct, especially with the really large telescopes we're trying to build today. And mirrors are less prone to those tiny imperfections in curvature and smudges and scratches that can really mess up lenses and cause drastic problems in our images. So they're just generally a lot more practical, so that's what's mainly used in astronomy today. However, I think refracting telescopes are a really fun way to introduce some basic and fundamental principles of optics that are really important to learn. So that's what I'm going to be talking about here. The first thing we need to understand is something called Snell's law. This is a law that governs how light bends when it passes from one medium into another, like from air into water, or in the case of a telescope, air into glass. All materials have something that is called an index of refraction, which is a number that governs how much light will bend away from or towards the normal, which is a line that is perpendicular to the surface of the material when it enters that material. The index of refraction for air is 1, water is about 1.33, and glass is about 1.5 or a little greater. Using this equation, we can figure out precisely the angle at which the light bends away from or towards the normal when it enters the material, as long as we know the indices of refraction and the angle at which it hits the material in the first place. When light passes into a material with a greater index of refraction than the one that it came from, it will bend towards the normal. And when it passes into a material with a lower index of refraction, it bends away from the normal. The greater the difference is between these two indices of refraction, the greater the change in the angle of the light beam will be. Now we need to apply this to the glass that is actually used in refracting telescopes, which is in the shape of a converging lens, like this. Our light beam hits the lens, and because the index of refraction is higher for glass than air, our light will bend towards the normal. Then the light will travel at this angle through the lens and come out the other side. The index of refraction is less for air than glass, so light will bend away from the normal. Because of the shape of the lens, in both of these cases, the light is being bent down towards the center of the lens. If we drew a bunch of these lines, we would see that they all bend towards each other and come together, or converge, at a point some distance away from the lens. This is how a converging lens forms an image. Fortunately, when we're trying to figure out how light rays bend to form an image with a converging lens, we have a little trick so we don't have to draw out every beam of light and calculate every angle to see how the image forms. When we're drawing a ray tracing diagram, we only care about 3 light rays, and how they bend is governed by the lens's focal point, which is half of the radius of curvature of the lens. One ray starts parallel to the optical axis, then goes through the far focal point. One goes through the near focal point, then parallel to the optical axis. The final ray just goes straight through the center of the lens and comes out at the exact same angle. Look where these rays converge. This is where our image is formed, just like this. We can see here how the image has been magnified by the lens, but wait, it's upside down? Plus, we would have to put a screen right at this point to be able to form the image, and that's not how telescopes work. So how can we use these lenses to design a telescope that will form magnified, upright images that we can see? We can fix the issue of the image not being upright by using 2 converging lenses in series. So when we create the diagram for the second lens, we'll start the light rays at the image created by the first lens instead of at the original object. That image will get flipped again, putting it back upright, as we can see in the diagram here. Now, there are a few other things we need to cover to fully capture the inner workings of a telescope. Typically, we'll use this equation to figure out how far away from the lens the image will form, or the image distance, and this to figure out how much bigger the image is from the original object. However, in astronomy, we're looking at a special case. Because celestial objects are so far away from us, we can approximate that object distance, the distance between the object, the celestial object, and the lens as infinity. In this case, the image distance is going to be equal to the focal length of the lens. And the reverse is also true, which will be important in a minute. If we put an object right at the focal length of the lens, the image will form at infinity. Essentially, the light rays coming out of the lens will be parallel to each other, and they'll never converge until you reach some distance infinitely far away from the lens. So normally we would look at the image on the far side of a converging lens by placing a screen at the point, right where the light rays converge, and we'll see a projection of the original object forming on the screen. But when light rays converge at infinity, this isn't possible. Instead, we can use that far lens in the series of lenses we were just talking about as an eyepiece for our telescope, and if you hold your eye right up to it, then you can see the image. For this to work in our telescope, the distance between our two lenses must be the sum of their focal lengths. Because celestial objects are a large enough distance from us that we can approximate it as infinity, the image from the first lens will form at a distance equal to its focal length away from that lens. Then we want the final image to form at infinity, so this first image must be a distance equal to the second lens's focal length away from that second lens. We add these two things together, and we get the necessary distance between the two lenses. With this setup, we're able to look straight into our telescopes and see magnified images.